Wonderful. Okay, so so being recorded and liable for everything you say. So thanks for coming, and we are looking forward to your talk. Thank you very much.
Great. Well, thank you, Jens. I'm very excited to tell you a bit about fault-tolerant quantum computing with photons. And I'd like to give you sort of an overview trying to answer two questions. One is, what does a large-scale photonic quantum computer look like? Or at least, what does the large-scale photonic quantum computer that Quantum wants to build look like? And two, how does it actually execute fault-tolerant quantum computations? So the most superficial answer to the first question, what does it look like, is this. For many people, the first picture that comes to mind when they hear linear optics is something like this picture on the left. But the components of a scalable photonic quantum computer look nothing like the aptly named chaotic-looking optical table.jpg that you can find on Wikipedia. And instead, they look much more like an ordinary silicon chip, because with integrated silicon photonics, miniaturized versions of all your favorite optical components like single photon sources, beam splitters, phase shifters, switches, detectors, they can all be fabricated in a semiconductor fab, same way other microchips are made. But this is not really the type of answer that is helpful here in the context of this talk. You see, with non-photonic qubits, or matter-based qubits, as we sometimes call them, there are many different types of qubits, like superconducting qubits, trapped ions, spin qubits, and so on. And pictures of these qubits, they all look very different. But conceptually, we like to describe them basically the same way, as arrays of static qubits on which we can execute gates and measurements. And the precise arrangement of these qubits and the available gates, they vary from hardware to hardware. For example, for superconducting qubits, a fitting description is often a large 2D array of physical qubits with more or less nearest neighbor 2-qubit gates and single qubit measurements, single qubit gates. But the more general principle here is that a large-scale quantum computer for matter-based qubit is often envisioned as a collection of static qubits on which you execute lots of gates, potentially billions of gates, until you reach the end of your computation. Now, to distinguish this approach from what's to come, we'll refer to this as circuit-based quantum computation. When you use photons as qubits, circuit-based quantum computation is not a very good description of your quantum computer, because photons can't really be used as static qubits. This is because of the following three main limitations, I would say, of photons in linear optics. First is that photons always travel at the speed of light, and when they do that on a chip, it implies that they're easily lost and short-lived. In the architecture that we'll look at in a moment, most photons actually only exist for a few nanoseconds, and the longest-lived photons, they exist for at most a few microseconds, meaning that at most a few microseconds pass between the generation of a photon and its measurement. But we'll see that this doesn't limit the duration of a full quantum computation, even if the computation takes several hours. Another difference between photons and static qubits is that photons are destroyed after measurements. When you measure a superconducting qubit, for instance, the superposition state, of course, of the qubit is destroyed as you project onto a computational basis state, but the qubit continues to exist. And that's not really the case for photons, where measurements are destructive. And finally, with linear optics, there's no way to perform deterministic entangling gates like CNOT gates between qubits. There are ways to perform probabilistic entangling measurements, but this is quite a severe limitation, and one of the main reasons why you need a different computational scheme to work with photons and linear optics. Now, circuit-based quantum computation is not the only known model of quantum computation. Another popular one is measurement-based quantum computing. In circuit-based quantum computation, the objects are single qubits, and entanglement is generated through the operations entangling 2-qubit gates. In measurement quantum computation, it's the other way around. A computation is performed by preparing a macroscopic entangled state called a cluster state, which can consist of billions of qubits in principle, which is then measured out by performing sequential single qubit measurements. So here sort of the roles are reversed. The operations, the single qubit measurements, they don't generate any entanglement, and instead all the entanglement is in the cluster state. But for the photonic architecture that we'll look at in a moment, neither circuit-based nor measurement-based quantum computing are good descriptions, really, because we neither have a static array of qubits, nor do we want to prepare a billion qubit state. Instead, we use a scheme where quantum computations are performed in a different way, and we call this fusion-based quantum computing. Word fusion here doesn't refer to the fusion of anyons or nuclear fusion, but to fusion measurements. These are probabilistic entangling few qubit measurements that can be done with photons and linear optics. There are different types of fusion measurements, but the one that we'll focus on today is called type 2 fusion. It's just a 2-qubit Bell basis measurement. So it's a measurement involving 2 photons, and the 2 photons are destroyed by the measurement, but the process doesn't measure the photons individually. It performs a 2-qubit Bell basis measurement. In terms of Pauli operators, you measure the 2-qubit operators x times x and z times z.
Can I ask a meta question and a scientific question at this point? The meta question is, can we ask questions along the talk, or do you want questions at the end?
Well, yeah, you can ask questions. Yeah.
Okay, then my next question is, I mean, you say type 2 fusion. It's not quite the original type 2 fusion, but it's a kind of a variant there of a basically use resources to get an as high probability as possible Bell measurement, right? So that's a bit of a variant of the original type 2 fusion. Will you kind of comment on that? Like, this is a bit of a deviation of the original schemes of photonic quantum computing. Is that something you will spend time on or comment on? Is that the right moment to ask this?
Oh yeah, I'll say more about this later.
Okay, good.
Just the introduction still.
Good.
Right. So, but in principle, you should think of what we want to do is we want to measure pairs of photonic qubits, and we want to get an x times x measurement outcome and a z times z measurement outcome. So it's an entangling measurement. So in some sense, in fusion-based quantum computation, both the objects and the operations are responsible for the generation of entanglement. And computations are performed by progressively generating more and more copies of few qubit entangled states that we refer to as resource states, and then performing fusions between pairs of qubits from different resource states. So the objects here are identical copies of entangled resource states. These are small constant-sized states consisting of perhaps tens of qubits or so. So it's not like the cluster state in MBQC whose size scales with the computation. And in a fusion-based computation, there's a sort of balance between resource state generation and fusion. Resource state generators provide a steady supply of resource states, adding qubits to the computation, and fusions between qubits from different resource states, they're used to remove qubits. And in some sense, teleport the quantum information from quantum information that's stored in older resource states into freshly generated resource states. And we'll see in a minute how this works in more detail. I just want to point out that all 3 of these models of computation, they're universal, and you can translate computations from one model to another. So no model is more powerful than the other. The question is just which model best describes the operations available to your quantum computer. And in our case, the natural operations turn out to be resource state generation and fusion. And you can read more about fusion-based quantum computation in the paper with the title Fusion-Based Quantum Computation, which you'll find on the archive. Of course, photons aren't all bad, and there are a few important advantages of photons. So before I show you the architecture, let me quickly mention the main advantages of photons that we want to exploit. The first is that operations are very fast. Timescales for single photon sources, switches, and detectors are nanoseconds. And the same is true for the classical CMOS control electronics. For comparison, the timescales with superconducting qubits are hundreds of nanoseconds up to microseconds. And for trapped ions, it's hundreds of microseconds up to milliseconds. So nanosecond timescales can be an important advantage. Second advantage is that photonic architectures are highly modularizable and scalable. Modularizable means that you can design a quantum computer as a network of identical modules that are connected through some kind of optical interconnects. And scalable means that these components can be mass-produced. Photons can travel large distances without any problems, so these networks don't even need to obey strict locality constraints like the one that you find for strict 2D arrays of static qubits, for instance. And the third advantage is one that I personally wasn't aware of before I started working with photons, but it's something that is actually very well known in the linear optics community, or perhaps optics community in general. There's a special kind of high capacity memory in some sense available for photons, and it's as simple as optical fiber. So the same stuff that brings high-speed internet to your home. Well, probably not your home unless you live in these exact 2 spots in Berlin, but I suppose many people's home in other places in the world. Anyway, optical fiber is mass-produced, cheap, and most importantly, has really low transmission loss. Commercially available optical fiber features transmission loss below 0.2 dB per kilometer. So what this means in concrete terms is that if a photon enters a 1 kilometer long optical fiber, there's a greater than 95% chance of it exiting the fiber 5 microseconds later. Speed of light in fiber is a bit lower than in vacuum, 0.2 meters per nanosecond. So it takes 5 microseconds to go from end to end. Turns out that such loss rates are low enough for quantum error correction. And what's more is if one photon enters this fiber every nanosecond, then this 1 kilometer long fiber can store up to 5,000 photons at any given time. So effectively, something as simple as a 1 kilometer long optical fiber can act as a temporary memory for 5,000 photonic qubits. Of course, it's a very peculiar kind of memory where qubits can only be stored for exactly 5 microseconds, and they can only be accessed in the exact order as they enter the fiber. But it still turns out to be a very powerful feature. All right, I'll now show you an architecture for photonic fusion-based quantum computing that takes advantage of these features. And I'll first spend a few minutes explaining what the quantum computer looks like, what the different components are, how they're arranged. And only afterwards, I'll tell you why this is a quantum computer and how you can use it to execute a quantum computation. So what does a large-scale photonic quantum computer look like? Well, it's not an array of static qubits, and instead it's a network of identical modules. Doesn't need to be a 2D network as shown here, but that's the simplest case. Each module in this network looks like this. You should think of modules as macroscopic chip-sized objects. Different modules in the network are connected using optical fiber. So here we have a network of modules. And we call these modules interleaving modules for reasons that will make more sense later, perhaps. Let's take a look at the components that you find in each of these modules. Each interleaving module consists of one resource state generator, which we abbreviate as RSG, a few delay lines, a few switches, and a few fusion devices, these boxes labeled F. And all these components are connected by waveguides. Let's go through all of these components. A resource state generator, or RSG, is a device that produces a resource state in every RSG cycle. If you like to think in terms of concrete numbers, think of one RSG cycle as 1 nanosecond. So in every nanosecond, each resource state generator in every one of these modules, and there's one resource state generator per module, produces a resource state, a specific few photon state. This RSG cycle is basically the physical clock rate of the quantum computer. In these pictures that I show, the resource state is a 6-photon state called a 6-ring, which is a 6-qubit graph state. You can think of it as the state that you get by taking 6 plus state and arranged in a ring and then applying controlled Z gates between nearest neighbors. But this is not necessarily how these states are prepared. And there are various ways to prepare them, which I'll comment on later. The resource state generator is actually a fairly complicated device. It's a very complicated component, and there's a lot going on inside. At the end of the talk, I'll say a bit more about what happens inside an RSG. But for the architecture, it doesn't really matter what happens inside the RSG box. So for now, we'll just treat it as a black box that emits 6 photons in a 6-ring state in every nanosecond. So the life of every photon in our quantum computer starts in a resource state generator and ultimately ends in a fusion device. As these 6 photons leave the RSG, they move along waveguides, drawn as lines in this picture. Each line actually corresponds to a pair of waveguides, so that each photon is a qubit, dual rail qubit. So if the photon is located in the top waveguide, it means that the qubit is in the 0 state. If the photon is in the bottom waveguide, it's in the 1 state. And as the photons propagate along the waveguides, some of them encounter a delay line, which is basically a very long waveguide. We call such a delay an N delay if it takes a photon N RSG cycles to traverse the delay. So a photon entering a 30 delay will exit the 30 delay after 30 nanoseconds. Think of these things as long optical fibers acting as some kind of temporary memory. A 30 delay will contain 30 photons, which are photons that have entered in previous RSG cycles. So for instance, as the photon that we have just generated enters the 30 delay, another photon will exit the delay, namely the one that entered the delay 30 nanoseconds ago or 30 RSG cycles ago. It's essentially a sort of first in, first out memory for photons. If this were a low loss optical fiber, it would be a 6-meter long fiber with 30 photons inside. Similarly, the 900 delay would be a longer fiber, like close to 200 meters long. since this is, yeah.
Sorry, and another question. When you said that there's a kind of a 95% probability of the photon coming out, but that includes all like complications like mode matching and whatnot. Like in a well-defined mode at a given instance of time, this photon will arrive at 95% probability, right? That's what you're basically saying.
Yeah. So this is the loss rate. Like, yeah. This refers to photonic loss. In principle, there are additional considerations like does it derive in the right? Well, no, like the
spatial mode and temporal mode and whatnot. But
yeah, but for optical fiber, silica fiber, it's 0.2 dB per kilometer, which is like 4.5% or so per kilometer.
But is this fiber here or waveguide? The delays.
So okay, so this is just a conceptual picture, right? Here you can here just says that we want a component that delays a photon for a specific time. So it's a long waveguide. How you implement the waveguide is in principle doesn't matter to the architecture, but it's of course advantageous for the waveguide to be a low loss waveguide. And the lowest loss waveguides, or among the lowest loss waveguides that we have, are optical fibers, because the propagation loss is extremely low in those.
But and what kind of coupling efficiencies do you get into the fiber and then back out?
Yeah, so a coupling efficiency.
Because the loss of the 0.2 dB is only in the actual fiber once you're in, right?
That's correct. That's correct. So I can't comment on like hardware specifics, but so I think in the literature you can find coupling loss rates into fiber of something like 0.1 dB, which is something that would eat into your loss budget inside the fiber. But this is not a hard limit, and one could imagine that if one were to be interested in using these fibers extensively with low loss rates, one would spend some time reducing the loss rate. But yes, the other loss matters too, but we'll get to that. We'll get to that later. So here's just to conceptually explain the components, and this is one of the components that we have is a delay that delays photons for a specific amount of time. So 900 delay would be the same thing, but it would take a photon 900 nanoseconds to travel inside this fiber. So as some photons enter a delay, other photons exit the delay. And the next components that our photons encounter are switches. These are active components that can be used to reroute photons to select their destination. Different switch settings basically correspond to selecting different target fusion devices. So for instance, with this switch setting, this photon goes to the top fusion device, but with the other switch setting to another fusion device. Some switch settings route photons to different modules. For instance, this switch setting routes this photon to this fusion device, but this switch setting routes the photon to a fusion device located in a neighboring module, namely the module to the left, this one, this module. So switch settings can be changed in every RSG cycle. And this is how we actually perform quantum computations. Switches are the only active component in this architecture. So when we talk about hardware instructions for our quantum computer, they aren't physical gates on static qubits, but instead switch settings for every RSG cycle. Let's say we choose these switch settings. One way or another, photons always end up in a fusion device at the end of their life. A fusion device is something that allows you to measure pairs of photons in different ways. There are actually additional switches hidden inside a fusion device. So two photons enter a fusion device, and the switch settings can be used to select how you measure these photons. You can either measure the photons individually, and here there are two ways of doing this, either a single qubit X basis measurement or a Z basis measurement, or you can measure them in an entangling two photon measurement. So this is the type 2 fusion, or the Bell measurement, which measures the two qubit Pauli operators X times X and Z times Z. This is a slightly simplified picture because in reality, you need at least one additional operation, namely a single qubit measurement preceded by a T gate, because you need at least one non-Clifford gate for universality. So this would be this pi rate rotation. In addition, it's also often useful to be able to perform Y measurements. But let's stick with this simplified picture for now. So after the photons are measured, we obtain the measurement results and the photons are destroyed. And this process repeats in every RSG cycle. So all RSGs generate a set of photons in a resource state. The photons enter a delay line, while other photons exit delay lines. Photons are switched into one of several fusion devices, where an additional switch decides the manner in which they are measured. And for every RSG cycle, we need to determine the right switch settings for these routing switches and the switches inside the fusion device to perform a quantum computation. In fusion-based quantum computing, essentially a computation corresponds to a set of fusion measurements between qubits from different resource states. And the point of this entire thing is to make sure that the right pairs of photons enter the same fusion device at the same time. And as it turns out, the network of modules shown here is a universal fault-tolerant quantum computer that allows you to execute quantum computations with surface codes. In the following, we'll see why that is. Specifically, I'll show you how you can take any quantum computation and translate it into switch settings for such a network of modules. Okay, let's first take a step back and review a few things about surface codes. So how does this whole process work if you want to execute a fault-tolerant quantum computation with an ordinary array of static qubits in a circuit-based quantum computing, so not fusion-based? I'll review a process for one specific flavor of surface code computation, namely lattice surgery. Basically, what if we want to execute some arbitrary large computation using an array of static qubits, and we want to use surface codes to do that? So basically, I'll give you a quick summary of the contents of this paper right here. As you can see, when I made the logo in 2019, I could not have anticipated that Game of Thrones would become completely irrelevant a few months later. But here we are. So let's say we have an array of static physical qubits, so a circuit-based quantum computer, and we want to execute some big quantum computation with 100 qubits and billions of gates. It's important to point out that these 100 qubits here in the circuit, they are logical error-corrected qubits because they need to survive for billions of operations, which could take hours to execute. So the array of physical qubits that we'll end up using, it won't consist of just 100 qubits, 100 physical qubits, but potentially hundreds of thousands of physical qubits that form 100 error-corrected logical qubits. But we'll get to that in a minute. The first step is to rewrite our circuit in terms of operations that we can actually execute with surface codes in lattice surgery. And here the natural operations are actually multi-qubit measurements, which we obtain so we want to translate this whole circuit into a sequence of only multi-qubit measurements. So measurements of multi-qubit Pauli operators. In this example, we start with some arbitrary Clifford plus T circuit. And we first rewrite our circuits in terms of other operations, which are called Pauli product rotations, e to the minus I p phi. So these are just a Pauli product operator is just a Pauli operator, product just to emphasize that it can be a multi-qubit Pauli operator. So example would be single qubit Z operator, or a 2-qubit X times Y operator, or Z times Z operator, or this 3-qubit operator, X times 1 times Y times Z. And I draw these things as boxes with the Pauli operator inside the box telling you the Pauli P, and phi being the angle of the rotation. So in concrete terms, for example, the S gate, the phase gate, is a Z pi over 4 rotation. The Hadamard gate can be written as a sequence of 3 pi over 4 rotations, Z pi over 4 times X pi over 4 times Z pi over 4. And the C naught gate is a Clifford gate like the previous two gates. So it can also be written in terms of pi over 4 rotation, but it's a 2-qubit gate. So it involves this big box over here. This is a 2-qubit rotation where the Pauli is Z times X. So it's Z times X pi over 4. And there are 2 single qubit rotations, Z minus pi over 4, X minus pi over 4. And the T gate is the pi rate rotation. So any arbitrary circuit can look like this. You have a bunch of Clifford gates, these orange boxes, pi over 4 rotations. You have a bunch of T gates, these green boxes, Z pi rate rotations. And at the end of the circuit, you have a bunch of measurements. Measurements are blue boxes with a Pauli inside the box telling you the basis of the measurement. And we'll be interested in translating this whole circuit into a sequence that only consists of blue boxes, but the blue boxes will not be necessarily single qubit measurements, but can also be multi-qubit measurements, like this is 5-qubit measurement here. So here's how you can do that. First thing you can do is you can get rid of all the orange boxes by commuting them to the end of the circuit. Reason you can do that is because pi over 4 rotations are Clifford gates. Clifford gates just map Paulis onto other Paulis. And there's a few very simple rules that allow you to move a pi over 4 rotation past another rotation. You just need to check whether the two operators commute or not. If they commute, then you can just move it past the other box. If they don't, then you need to change the Pauli in the box by multiplying these Paulis together. For instance, x minus pi over 4, this rotation doesn't commute with the z here. If I want to move it past it, it turns the z rotation into a y rotation, or minus y rotation in this case. And the same trick can be used to absorb Clifford gates into measurements, changing the measurement basis in the same way. So these x rotations turn the z measurements into y measurements. And when you do this sort of thing, you can also turn single qubit operations to multi-qubit operations, like this x11z pi over 4 rotation doesn't commute with this z operation here, and it turns it into a 2-qubit rotation when you commute it past the gate. So now it's a 2-qubit rotation, and the same can happen to these measurements. Single qubit measurements can turn into 2-qubit measurements. For instance, here we have generated a ZZ measurement and an XX measurement, so a Bell basis measurement in some sense. And this is something that you can continue doing until you're left with a circuit that only contains pi over 8 rotations and these multi-qubit measurements. So any quantum computation can be described that way, as a sequence of only pi over 8 rotations and a bunch of measurements at the end. And the number of pi over 8 rotations in the circuit is equivalent to the T count of the circuit. So there can be quite a lot of those in a useful computation. Could be a sequence of billions of these things. So I said that we want a circuit that only contains measurements. And one way to replace these pi over 8 rotations with measurements is to use magic states. So here's a circuit identity that tells you that if you want to execute a pi over 8 rotation, this multi-qubit rotation, then you can do that by initializing a magic state, which is a state that is 0 plus e to the I pi over 1. So it's a plus state on which you've applied a T gate. And then you just need to perform a multi-qubit measurement, P times Z. Based on this measurement outcome, there's also a single qubit measurement, which depending on the outcome is an X or a Y measurement. Based on this outcome, there's a Pauli correction, but Pauli corrections are just classical corrections, so they're not real operations. That's just to say that there's a circuit identity that you can use to replace, for instance, this ZYX1Z pi over 8 rotation with a ZYX1Z times Z measurement on a magic state, which is then sort of destroyed by the single qubit measurement. So each T gate takes a magic state and a measurement, and that way you can have a circuit that to summarize, any quantum circuit can be transformed into a circuit that consists of only 2 types of operations: preparation of magic states and multi-qubit Pauli measurements. And that turns out to be very natural for lattice surgery and surface codes. Now, we want to execute these circuits in a fault-tolerant way using surface code qubits encoded in surface code patches. And to plan the different logical operations that you're going to execute on your logical qubits, it's useful to draw the arrangement of logical qubits and their configuration, or how their configuration changes with every logical operation that we perform. So here, these drawings are called lattice surgery diagrams, which are meant to describe the operations that we need to do on our array of static qubits in a coarse-grained way. So the diagram consists of a board partitioned into a number of tiles, where each tile represents d by d physical qubits. D is the code distance, which is a parameter that depends on how much error suppression you need. And in this case, d equals 5. So on these tiles, we can place patches, and patches represent qubits, logical qubits. These patches have 4 corners and 4 edges, 2 dashed edges, 2 dashed edges and 2 solid edges. And each dashed edge of a qubit represents the qubit's Pauli X operator, and each solid edge, the qubit's Z operator. There's no edge for the Y operator because Y is just the product of X and Z. Patches can be drawn in different shapes and sizes, and these square patches drawn here are just the simplest example. For our purposes, it will be actually simple to consider these rectangular patches instead. They still have 2 dashed edges and 2 solid edges, but the edges are arranged a bit differently. So each such rectangular patch is still 1 qubit. On the level of physical qubits, each patch corresponds to some arrangement of check operators that you need to measure. Each of these squares is a check operator, and the yellowish squares are products of Z operators on the 4 qubits at the corners of the square. and the gray squares are products of X operators. So a quantum computation with surface codes is performed in so-called code cycles. In every code cycle, you need to measure all of these shown check operators exactly once. Logical operations are essentially performed by changing the arrangement of check operators that you measure from cycle to cycle. So for instance, in one cycle, you might measure this arrangement of check operators, in the next cycle, this arrangement, and then in another cycle, this arrangement. So if you're not very familiar with surface codes and these check operators don't make much sense to you, don't worry about that, because this won't be that important for the main message of this talk. And it's really fine to look only at this coarse-grained picture of lattice-Sergi diagrams. All I want to say here is that when I draw these pictures, there is a specific prescription to translate these pictures into physical operations. Okay, so what is lattice-Sergi? The simplest way you can arrange the logical qubits of your quantum computation is in a line, one next to the other. So a 100-qubit quantum computer would contain 100 rectangular patches next to one another, or 10-qubit quantum computer, 10 patches. For simplicity, we'll look at a 5-qubit quantum computer. And as mentioned before, you execute operations with surface code patches and cycles. In every sort of logical cycle, you change the patch configuration. You perform Pauli product measurements by merging patches into one big patch in a specific way. And this is called lattice-Sergi. The way it works is that you use this extra space below your row of qubits to connect them to one big patch, connecting them using the X edges and Z edges of the qubits. So for instance, if you want to measure this operator, Z1 times Y2 times X3 times Z5, you merge through the first qubit's Z edge, the second qubit's X and Z edge, because Y is the product of X and Z, third qubit's X edge, and the fifth qubit's Z edge. So here's another example, X1 times Y3 times Z4. Here's the measurement of Z1 times Z2. And this is sort of how you can perform one of these Pauli product measurements, one of these multi-qubit measurements after the other. Of course, there's one ingredient missing, and that's the preparation of magic states. Now, you can prepare magic states with surface codes, but there's a problem. There's no simple way of doing this that is fault tolerant. When you prepare a magic state, there's always a certain probability that the state is affected by an error. Let's say 1% probability in this example. This means that in this example, 1 out of every 100 magic states that you prepare is faulty, and you're not told when this happens, which is of course unacceptable, because this implies that 1 out of every 100 operations that you execute using these magic states will be wrong, and you have billions of operations to execute. Of course, many of you will be familiar that we have a way to filter out faulty magic states, and it's called magic state distillation. So instead of using faulty magic states, we need to add some additional part to our quantum computer that sort of acts as a source of good magic states, which is this distillation block here. If we look inside the distillation block, we see that it's basically just it's the same, it's more of the same component of that we had before. It's basically just a small quantum computer that is repeatedly executing the same short computation. Magic state distillation is just a very small quantum computation that uses many bad magic states to produce one good magic state. Here's an example of a distillation circuit, but it doesn't really matter how it works for us today. It's just to show that it looks the same as every other circuit. All you need to see is that the circuit contains 15 green boxes, and at the end of the circuit, you're left with one magic state. Remember that each green box requires a magic state to execute it, but here you don't need perfect magic states, you use 15 faulty magic states. So for instance, if we execute it using 15 magic states that have a 1% chance of being faulty, we can produce a magic state that has a like a 10 to the minus 5 probability of having an error. And if that's not good enough, we can send these improved magic states to another round of distillation to improve their error probability from 10 to the minus 5 to 10 to the minus 14. And there are many distillation protocols like this, not just 15 to 1. Basically, what this just means is that your quantum computer consists of 2 parts, or can be made to consist of 2 parts. One part that sort of stores the qubits on which you perform the computation, which is the part that we have here. And in addition, a smaller additional part right here that is always performing the same short computation, namely the generation of good magic states. In practice, there can be more than one distillation block to make sure that magic states are produced fast enough. The way these operations then look like is that you load a magic state from the distillation block and then just perform a PPM same way as before. So you measure out this magic state, repeat the same procedure for the next operation. And all of this can be done in one sort of cycle, as with the previous PPMs. Okay, so this was sort of a brief overview of how you execute logical operations with surface codes and latticeology when you have a circuit-based quantum computer. But how does this work for fusion-based quantum computing? We'll look at a simplified example, still for circuit-based quantum computing for now. Suppose we have a 4-qubit quantum computer, and we're only interested in performing Pauli measurements involving the z operators of the 4 qubits. So we just have 4 simple square patches with their z edges pointing downwards here. In this example, the code distance is 9 instead of 5, so patches are a bit bigger. If we want to measure z2 times z3, we would change the patch configuration to this one. This would be latticeology. Now, one thing I didn't mention before is that every time you change the patch configuration like this to perform a latticeology operation, you perform more than one round of measurements. You actually need to repeat these measurements multiple times, because with physical operations, the measurements themselves can be faulty too. So in most cases, you repeat the measurements d times. So for this z2 times z3 measurement, we measure all these check operators, not only once, but also in the next code cycle, and in the next, and in the next, until we have done that for 9 code cycles. In this space-time picture on the right, we basically keep track of the history of measurements that we have performed. When we perform the next logical operation, say a z1 times z4 measurement, we change the patch configuration and again repeat these measurements for 9 code cycles. Of course, this is still a circuit-based, a picture for circuit-based quantum computation. So why am I telling you this? Because it's only a small step from this space-time picture on the right to a picture that is more useful to us. Remember, the hardware that we're considering consists of these interleaving modules that produce resource states and fuse pairs of photons. So hardware instructions should tell us how many resource states need to be produced and which photon pairs should be fused. These pictures don't do that. Instead, we use a different type of diagram that we call a fusion graph. And here's how it's generated. So the logical operation that we'll be considering is still the same as before, just 4 square patches encoding 4 qubits. And we first measure z2 times z3, and then z1 times z4. To translate this into resource states and fusions, it's useful to write down a graph that shows you how many resource states need to be produced and how they should be fused. And this graph is a so-called fusion graph. I'll first show you how it is generated, and then I'll explain what this graph actually means. So we're generating a 3-dimensional cubic lattice layer by layer. Of course, each layer of a cubic lattice looks like a 2-dimensional square lattice. This lattice consists of vertices and edges, so just connections between vertices, but there are also these broken edges. We call edges that are connected to only one vertex half edges. And we're choosing these layers such that they sort of mimic the pattern described by the arrangement of logical qubit patches. So for instance, here there are 2 patches that are disconnected from the rest of the lattice, but these 2 patches are connected with some, with some broken edges along the middle. As with the patch diagrams before, there are very specific rules to translate these pictures into fusion graphs that will make sense to people familiar with surface codes. But here I just want to show you the general pattern. So for now, just notice that the pattern of edges and half edges is related to the patches and connections described by this figure. So this cubic lattice that we're producing is directly obtained from these pictures in principle. Every patch contributes d by d vertices to the layer, where in this case d equals 9. And we continue generating the cubic lattice, adding these layers until we have a lattice with 9 layers, or general d layers. This describes our first logical operation, the measurement of z2 times z3. Now we perform the next logical operation. We keep adding layers, but this time the layers look different. They mimic the pattern of this new configuration. So there are like half edges here. And again, we keep doing this until we have 9 layers. And this process repeats for all logical operations. So this fusion graph right here corresponds to the 2 logical operations described by these pictures, but how do we read it? In a fusion graph, each vertex, so each of these vertices shown here, corresponds to a resource state. Remember, we're considering resource states made of 6 photons. So each vertex here actually corresponds to 6 photons, 1 for each of the 6 directions of the 3D lattice. Let's call these directions north, east, southwest for the in-plane directions, and up and down for the z direction, essentially. We can also label the 6 photons of each resource state, north, north, up, east, south, down, west. Two vertices are then two resource states. And a connection between vertices means that the two photons, the two qubits along this connection, they need to be fused. So for instance, an edge between these two vertices means that the east photon of this resource state needs to be fused with the west photon of this resource state. Or the up photon of this resource state needs to be fused with the down photon of this resource state. Specifically, it means that these pairs of photons need to end up in the same fusion device at the same time. And also, when you have half edges, it means that the photon is not fused with another, but simply measured in a single photon measurement. I should mention that these are slightly simplified versions of fusion graphs. So when you have a single qubit measurement, these things don't tell you if it's an X or Z measurement. In the slightly more complicated version, you can also use the graph to determine if it's X or Z. But I'll briefly comment on that later. So this graph right here, to summarize, tells us to generate all these resource states and fuse their photons according to this very specific prescription. There are concrete hardware instructions for a device that produces resource states and fuses photons. And all that's left to do is to figure out how we can do this with our interleaving modules. Let's go through an example. Before I showed you an interleaving module with 30 delays and 900 delays, but this was just, these were just example numbers. In general, we have L delays, we have 1 delays, L delays, and L squared delays, where this number L is called the rastering length. For now, let's look at an interleaving module with L equals 6. So there's a 1 delay, a 6 delay, and a 36 delay. These will be our interleaving modules, and we'll consider a network made of 18 of these modules arranged in a 6x3 grid. Our hardware will be executing these instructions layer by layer, generating all resource states of one layer of the fusion graph before moving on to the next. So even though we need to generate all of these resource states, we're not going to generate them all at the same time. We're going to generate them layer by layer. Of course, each layer consists of lots of resource states, but our network only contains 18 modules that only produce 18 resource states at a time. So it will take multiple time steps to execute the instructions of each layer. Let's look at this layer, for example. First step is to divide this layer into squares of size L by L, in this case, 6 by 6. Each square will be handled by one of these interleaving modules, meaning that all resource states contained within one square will be produced by one module. Of course, a module only produces one resource state at a time, so we must also specify the order in which they're generated. And here, the top left resource state in each square will be generated first, and the bottom right resource state will be generated last, going from left to right and line by line, essentially. So we're sort of like 3D printing this lattice. There are 36 resource states in each square, so executing these instructions of one layer will take 36 RSG cycles. Let's focus on one specific module, this square right here. This square of the fusion graph contains all the hardware instructions relevant to this module. Remember, the hardware instructions that we're looking for are switch settings, and there are two decisions to be made here. The first is this question of routing the photons to the right fusion device, which is done by these switches. I've added the labels local and network here to the different output ports so that every switch needs to decide between the two options, network or local. And secondly, each photon sees a switch inside the fusion device to decide the manner in which it is measured. So here there are three options. There's fusion, which is this 2-photon measurement, or X or Z, single photon measurements. For every photon produced in the RSG, we need to decide what happens to it when it counters these two switches. Basically, it's like that for every photon that we produce in the RSG, we need to assign it a passport, which either says network or local, and either fusion X or Z. We can use the fusion graph to directly read off which passport we need to assign to which photon. Decision-making is actually fairly simple because if the photon is part of an edge that crosses a boundary between squares, then you select network and fusion. And if the photon is part of an edge contained within a square, you select local and fusion. Remember, each vertex in this graph is a resource state corresponding to 6 photons, right? So the photons are in some sense placed around the vertices. If the photon sits on a half edge, then you select local and X or Z. Again, from this graph, because you can't tell whether it's X or Z because I'm showing you a slightly simplified version, but don't worry about this detail. All that matters is that a half edge means single photon measurement. So this part could be a bit confusing. So let's go, let's see how this process works. In the first cycle, our RSG produces a resource state, specifically this resource state number 1. Let's first look at the east photon. According to the fusion graph, it needs to be fused with the west photon of resource state number 2, which doesn't exist yet. The corresponding edge is contained within the square, so the east photon is part of a local fusion. So we select local and fusion. Of course, the east photon will only encounter these switches in the next cycle because it first enters a 1 delay. After all, it needs to be fused with a photon that doesn't exist yet, but will only be produced in the next cycle. The west photon is part of a network fusion. So we select network and fusion, and it enters the switch immediately, where the network option sends it on its way to the neighboring module to the west. The south photon participates in a local fusion, but again, its fusion partner will only be generated in the future in cycle number 7. So it first enters a 6 delay. And the north photon is part of a network fusion, so the switch sends it to the neighboring module to the north. And finally, we have these up and down photons. These are part of fusions between different layers. They don't have a network option, so it's always the same fusion. So you cannot see these these up and down photons from this picture. They're sort of the edges that live between layers, right? So when you look at one layer, you don't see that. The up photon needs to fuse with a down photon from the next layer. But this photon will only be generated once we're done with the current layer, which will happen in 36 cycles. So it enters the 36 delay. Similarly, the down photon is used with a photon that was generated in the previous layer, 36 cycles ago. And at this very moment, this photon will be emerging from the 36 delay to be fused with a down photon.
I see. And a question, I mean, this cannot be avoided, right? I mean, you will have these like 36 type long delays when going from one complete layer to the next, right? So that cannot be optimized. So in either way, you will have these like extremely long delay lines.
Well, the length of the longest delay actually depends on how, we'll see in a moment, it depends on how many hardware components you want to use, because the longer you pick these delays,
yes,
the bigger the slice, the slices that you can produce. Yeah. Essentially, if you have very long delays, you need fewer modules. If you have very short delays, you need more modules. This thing could have also been a 1 delay, in which case there would have been a module for every single one of these resource states in a slice.
Okay.
This would be sort of the situation analogous to an array of static qubits.
Okay, thank you.
So these were all the operations that we needed to do in the first RSG cycle. And if this was confusing, perhaps the second cycle will help a bit. In the second cycle, the RSG again produces 6 photons. The east photon is again part of a local fusion, but first enters a 1 delay. This time, the west photon is also part of a local fusion. It fuses with the east photon that we have generated in the last cycle. Remember, this was the photon that we had sent into the 1 delay. And this east photon from the last cycle will now be emerging from the 1 delay so that the west photon can fuse with it. So the point of all these delays is to make sure that the right photon pairs arrive at the same fusion device at the same time. And, so here was a situation where we had a 1 delay, for instance. The south photon is again part of a local fusion, and the north photon is again sent away for a network fusion, and the up and down photons again perform the fusions involving resource states from different layers. So if you didn't get the details, that's fine. I guess what matters is to show that the type, to show the type of decision making that is going on here, namely the selection of switch settings using a fusion graph. And this is the same process that we repeat for every single cycle. In cycle 3, there will be a half edge. So for the east photon, we'll be selecting a single qubit measurement instead of a fusion. In cycle 4, the same will be true for the west photon. Eventually, we'll reach cycle number 7. In this cycle, well, something slightly more interesting happens because we'll finally get to start fusing the south photons that have been piling up in the 6 delay, because the north photon from cycle number 7 is part of a local fusion, and it fuses with a south photon that has been produced in cycle number 1, so 6 cycles ago. And this photon will be the one that's sort of leaving the 6 delay just now to be fused with the north photon. And you do this again and again and again until you reach cycle number 36. And after cycle 36, you're done with this layer and move on to the next, repeating the same steps over and over again. So there was quite a bit going on here. But to summarize, this network of interleaving modules implements, so we go through, So once we're done with this slide, we would be going on to the next slide. That's what I was going to say. So this network of interleaving modules, it implements surface code operations equivalent to this arrangement of 4 logical qubits. It can generate fusion graphs one slice after the other. And if you count carefully, then each of these 2D slices, it contains 648 resource states. The surface code computation that is executed is equivalent to a computation that could be executed by 648 physical static qubits. But we use 18 interleaving modules. So 36 times fewer modules than qubits. And this 36 is exactly what sort of Jens commented on before. This 36 is the length of the longest delay, which is L squared equals 36. And we refer to the use of long fiber delays to reduce the number of hardware components that we need as interleaving. And this is all about playing around with this rastering length L. The example that we looked at used 18 modules with L equals 6. And if each cycle takes 1 nanosecond, then this corresponds to a longest fiber that is only 7 meters long, 7.2 meters. But of course, we could have interleaved less in principle. With L equals 3, we could have done the same thing with 72 modules and a maximum delay of only 1.8 meters. But of course, we're much more interested in the opposite regime, because with a large rastering length, L, we can drastically reduce the number of components that we need for a large-scale quantum computer. In this example, you would need only this example for L equals 18, you would need only 2 modules, but a maximum delay length of 65 meters almost. So here we have a savings factor of 324. The limit is set by how much loss you can tolerate from fiber delays. And it turns out that you can push it even further. It's even reasonable to push the longest fiber length to 1 kilometer and beyond, in which case L squared equals 5,000. So to reiterate what this means is when you use 1 kilometer long fibers, you can get this sort of resource savings factor of 5,000. In other words, a quantum computer that's equivalent to a 1,000,000 qubit array of static qubits is equivalent to a network of 200 interleaving modules that use 1 kilometer long fibers. Here's how we know that 1 kilometer long optical fibers are a reasonable thing to consider. First of all, one thing that I didn't mention is how we assemble check operators from the fusion measurement outcomes that we obtain. Because when we fuse pairs of photons in a Bell basis measurement, it produces 2 measurement outcomes. And these measurement outcomes are very important because products of these outcomes correspond to check operators that can be fed into a surface code decoder. If you read the paper about these interleaving modules, then you'll find that the fusion graphs shown in the paper all look like this. There's still cubic lattices as before, but there's some extra information in this diagram because there's some colors assigned to cubic volumes. And I won't go into detail here how to read these graphs, but I'll just say that these more detailed fusion graphs tell you how to assemble fusion outcomes to check operators, also tell you which single qubit measurements are X or Z. And for those of you who are familiar with surface codes, I have some additional slides with a lot more details that I can show you after the talk if you'd like to know more about these fusion graphs. But I decided not to show this here because I suspect that people who haven't worked with surface codes before won't find this very illuminating. Anyway, we performed some numerical simulations to study the loss threshold of this scheme and how long we can make these fibers. Well, I personally didn't perform the numerics, but my colleagues did. And a few words about the error model here. If you have heard about type 2 fusions before, you'll also know that they only succeed with 50% probability. So only with 50% probability, you obtain both the XX and the Z outcome. And in the failure case, you only obtain one of the outcomes. And that's actually not good enough. There are 2 things that we can do to increase the success probability. First of all, there's a boosted version of type 2 fusion, which consumes an extra Bell pair that increases the success probability to 75%. But the second thing that we do is that we replace each qubit of the 6-ring resource states with 4 qubits that sort of form a small distance 2 code. So each photon is actually 4 photons, and it's not a 6-photon resource state, but a 24-photon resource state. Essentially, this gives you multiple attempts to perform fusions and further suppresses the failure.
A question on this. So I mean this fusion idea of using an extra Bell pair is kind of interesting and came strangely late in history, right? That's a pretty recent a proposal, but you can also beef this up further, right? I mean, you can make use of more sophisticated resources to get the probability of success even higher than 75%. Why is that not used? I mean, that seems also a reasonable idea. Instead of the encoding one photon into like 4 and then having several attempts. I mean, what's the trade-off?
So first of all, you sort of want to use as few resources as possible, and here we want to push the there are two things that play a role in this scheme, and they're sort of treated on equal footing. One is the success probability of fusions, and that is sort of something that we're boosting as advantageous. But the other thing is the loss probability of fusions. And if, the more photons you use, that's actually, depends on how you use that, but that can be disadvantageous. And there's also the Pauli error probability, and that can also sort of suffer if you use more photons in a way that doesn't form a code like this. So in this case, we used boosting to the point where we push the failure probability below the sort of loss rate that we encounter. Mm-hmm. But you're right. There are a lot of tricks that you can sort of consider. Also, different resource states, different fusion circuits that allow you to improve this scheme. So it's not meant to be sort of a best proposed.
Okay. It also deviates a bit from the purely ballistic mindset from like the old days, like where there was the idea of like using other resources to use like percolation ideas or so to improve things. So that's not really pursued so much.
No, that's not what we're doing here.
Can I ask a question?
Yeah.
Normally, or I guess for static qubits, at some point, if you want to do like a non-Clifford gate, I think you have to correct like your qubit errors. What does that look like in such an architecture as here?
If you want to perform, so first of all, if you want to perform a non-Clifford gate, there's also some sort of fusion graph like that, but it will involve one special edge that corresponds to a single qubit measurement, where on the single qubit you need to apply a T-gate before you perform the measurement. So that would be, I don't know, if you're familiar with surface codes, that corresponds to state injection, which is the protocol that prepares a magic state. Now, when you work with surface codes, correcting errors is not an operation that you perform on the quantum computer. Error correction is something that you can, you measure these you extract these error syndromes by performing these measurements that allow you to, there's never a sort of a physical operation that corresponds to correcting an error.
Okay, yeah, you can just check a Pauli frame, but.
Yeah, exactly. Essentially, the decoding just tells you, all the logical operations that you perform, there are these multi-qubit logical measurements, and decoding just tells you how to interpret these measurements, right? You need to somehow assemble these measurement results from physical outcomes, and decoding is sort of the process of determining, is the measurement outcome of the logical measurement +1 or -1? Other than that, there's no sort of physical operation for Pauli corrections or anything like that.
Okay. Thank you.
Right. Okay. So
the follow up on this. You have this fault-tolerant architecture that implements a code that extracts syndromes, but I mean, in this circuit model, you would have this recovery operation, right? You do the decoding and then you kind of apply like a correction. But here it seems like you perform measurement and everything's gone and there's nothing you can do about it. So how?
Well, I mean, it's actually very similar to the case that you actually do in the circuit-based setting, because in the circuit-based setting, the way you perform decoding, you don't actually perform it on a 2D lattice. You actually do perform it on a very similar thing, which is a space-time diagram. And your recovery operations are sort of, so the space-time diagram in the circuit picture consists of this measurement history of check operators over multiple layers. And so in that case, the recovery operations would be sort of, flips of qubits and measurements. In this case, it's a very similar thing because, for every edge in this graph, we have a measurement outcome. So every edge gives you sort of a +1, -1 value. And these are values that can be flipped. So there's a recovery operation, which is sort of the flipping of measurement outcomes. Yeah, I don't know if was that sufficient detail, or I can tell you more about that later. But
so what I'm saying is like you just change the measurement result classically, instead of in the circuit model you would actually kind of like.
Oh, no, you even in the circuit model, you would never really apply any Pauli recovery operation to your qubits because it's completely unnecessary. Because Pauli corrections are things that you can just track classically. A recovery operation.
Sorry. Yeah, you're right. Yes.
So flips, Pauli flips, you never really do because that would be sort of unnecessary effort and dangerous.
I mean, but this only works for algorithms where you measure out all the qubits in the end, because you basically, you could do a quantum recovery operation, but since you are measuring all the single qubits in the end anyhow, you just shift the recovery operation into the measurement.
Yes, but every quantum computation is like that, because in the end, all we can extract from a quantum computation is classical information, which is the result of the computation. So, in some sense, you have a circuit, which is your quantum computation. At the end of the circuit, there are a bunch of measurements, which are the result of the computation. And all your sort of classical tracking of the recovery operations is just sort of a way to obtain the values for the result of the computation.
I see. Okay. Yeah, I was thinking about along the lines like just looking at a quantum memory itself, but you can view it as an identity operation for a very long time. So
yeah, that's right.
Okay, thanks.
Eventually, you'll always measure your qubits. Okay, so I have a few more. Well, I'll just quickly go through it. So for this 4-qubit thing, I'll just say that the modules still look the same as before, but if we use 4 qubits instead of if every photon is replaced with 4 photons, this means that there are just 4 times as many waveguides and switches and fusion devices. Or alternatively, the modules still look exactly the same, but each RSG cycle turns into 4 cycles. In any case, the error model here is that each photon that we produce has 2 sources of loss. There's the baseline loss, which is the probability that the photon is lost in the RSG or in the switch or in the fusion device. So this is loss that is the same for all photons. And in addition, there is the loss that is due to the delay that the photon enters. And this loss is different for all photons because some photons enter 1 delay, others an L delay, others an L squared delay, and others no delay at all. The larger we pick L, so the longer we make the delays, the less baseline loss the architecture can tolerate. So for delays, we assume that the loss probability is 0.2 dB per kilometer, as in commercially available fiber. So in some sense, the coupling loss is part of the baseline loss. And with L equals 1, or I guess that's not exactly true because not all photons need to enter a fiber. Anyway, so with L equals 1, the baseline loss threshold is 2.7%. So the photon loss probability needs to be below 2.7% for error correction to be possible in this specific scheme. And we find that an L squared of 5,000, so 1 kilometer long fibers, decreases the loss threshold only a little bit to 2.3%. But as we make delays longer and longer, sort of, this becomes impossible at some point. So at 30,000, the loss threshold comes close to 0. But 1 kilometer long delays are actually something that is reasonable to consider. So here we only studied the loss threshold because loss is the dominant source of error for photons. Of course, the code can also correct Pauli errors, but these are actually much less of a concern with photons. Another thing that you can read about in the paper, but I didn't get to mention in the talk, is that these networks of interleaving modules provide you a lot of flexibility in the types of logical operations that you can implement. And connections between modules, they're long optical fibers, so they are not limited to 2D arrays. And you can instead consider crazy non-local connections between modules. And there are a few basic examples in the paper showing that you can achieve many interesting things with that. For instance, you can implement periodic boundaries, or you can remove redundant volume from the computation when you move qubits from place to place, or you can implement some sort of exotic geometries that you would find otherwise difficult to implement. These are just some examples that are meant to show you the tools that you have at your disposal, but we believe that there's a lot more that can be done with that. Now, some final remarks about the resource state generator that I showed you. So I showed you that you can effectively get a 1,000,000 qubit quantum computer with a network of only a few hundreds of these interleaving modules. And perhaps you might get the impression that this implies that, for this reason, this 100 module quantum computer is a very small device, but it's not. We've treated the resource state generator as a black box that outputs a 24 photon resource state every nanosecond. And generating such entangled states within your optics is actually not so easy. And in fact, almost all of the complexity in building this device is hidden inside this RSG box. With silicon photonics, it's possible to generate single photons. In addition, you can take multiple photons and probabilistically generate small entangled states. For example, there are linear optical circuits that allow you to probabilistically generate 3-qubit GHZ states from single photons. And we call such small entangled states seed states, a device that produces such states probabilistically a seed state generator. If you have many such seed states, you can use fusion operations to produce larger resource states like 6 rings. So what goes on inside an RSG is more than one might naively expect, because an RSG is actually a collection of many, many seed state generators. Still something that's modular, because these are just identical components that can be mass produced, but there are many of them. So many, in fact, that even though we only need perhaps a few hundred of these interleaving modules for a 1,000,000 qubit device, we still expect the full quantum computer to be a data center sized device. And there's a lot of work at PsiQuantum that goes into clever schemes for the generation of small entangled states. And while I won't say more about this here, there's a paper coming out in a few weeks that explains this in much more detail. Now, you might be thinking, generating 20 or so qubit states, how can this be so difficult? Superconducting qubits do that all the time. And in a sense, so this is the last thing I'll say, in a sense, the challenges of photonic qubits are the inverse of the challenges of matter-based qubits. Because with photonic qubits, modularity and scalability and long-range connectivity are sort of the easy part, at least with silicon photonics. But the generation of small-scale entangled states, that's what the main challenge is. Of course, nothing about building quantum computers is easy, so it's easy in quotation marks. But for matter-based qubits, like superconducting qubits, generating small entangled states like GHZ states or larger states is something that existing devices can do without problems. But making long-range connections without modularizing, making long-range connections and modularizing, scaling up, that's hard. Something that I find very exciting about this architecture is that in principle, it's compatible with non-photonic qubits, because the RSG is a black box and it doesn't really matter what goes on inside for the architecture. It can be made, it can be made from silicon photonic components, but doesn't have to. It just needs to be a device that emits entangled photons in periodic time intervals. And in principle, it could be a matter-based device, like a superconducting qubit chip with transduction to photons. So perhaps in the future, we might be able to have a quantum computer that sort of combines the best of both worlds: efficient entanglement generation from matter-based devices and scalability and long-range connectivity from silicon photonics. And in this case, interleaving modules and silicon photonics provide an alternative path towards scaling up matter-based qubits. So instead of trying to build large connected 2D arrays of millions of qubits, this would shift the challenge to building many identical few qubit devices that always perform the same operation, resource state generation. But they need to be capable of transduction to photons. So they must be able to swap the state of their qubits into a photonic state. And that's not necessarily an easier way to scale up a matter-based qubit device, but an alternative way, because achieving high fidelity transduction to photons is something that's very difficult too. But if it works, you could have sort of this device in which the components made from matter-based qubits are only responsible for the microscopic part of the quantum computer, resource state generation, and the photonic components handle all the rest. So to summarize, I've shown you an architecture for fault-tolerant quantum computing with surface codes in which the quantum computer is a network of modules that we call interleaving modules. And each module consists of resource state generators, a few fiber delays, switches, and fusion devices, which in turn contain switches and detectors. Resource state generators can be built from silicon photonic components, but in principle can be any device that produces photonic resource states in periodic time intervals. And with networks of interleaving modules, you can do anything that you can do with any other surface code quantum computer. By taking advantage of these long fiber delays as temporary memory for photons, the number of modules in a large-scale quantum computer can be much lower than the number of physical qubits that you would need in an array of static qubits. Also, connections of these modules don't need to be to the nearest neighbors, but more non-local connections can improve the performance of logical operations and also allow you to implement exotic geometries. So you can read more about this in our paper, Interleaving, Modular Architectures for Fault-Tolerant Photonic Quantum Computing. Credits go to all my colleagues at PsiQuantum, particularly Naomi and Fernando, who together with me spent a lot of time to put together a hopefully enjoyable paper. But many of the ideas that went into this paper existed before I joined the company. I'm just the lucky one who gets to tell you about this. So credits also go to Hector, Isaac, Mihir, and Sam, and Terry. And there's also a paper explaining the mathematical framework of fusion-based quantum computation that was published in January, and it's called Fusion-Based Quantum Computation. You can find it on the archive. Here's a picture of the architecture team at PsiQuantum from the before times. Maybe you recognize some familiar faces. I hope you enjoyed the talk. There are some bonus slides for those of you who are surface code enthusiasts and want to chat more about fusion graphs, but that's for later. So if you have any more questions, now is the time.
Yeah, wonderful. First of all, clap, 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 clap. Thanks for the great talk. I will stop the